Hi everyone, this is a special video today. This is special because many of you who have not been sailing on LNG carriers struggle to answer questions related to this type of ships during your oral examination. That's why I thought I will summarize the LNG carrier cargo operations in one video. It might be a bit lengthy for your taste, but I have summarized it especially for those of you who have not been sailing on these kind of ships. Of course, if you have been sailing on ships, I am sure that you know a lot more than me and feel free to add to the knowledge that is provided to this video so that all of you can learn from one another. So without wasting your time, let me get started because this video is going to be a bit lengthy in size. So liquefied natural gas carriers or LNG carriers is what we are going to be focusing on because this is a type of ship transported in a double hull specifically designed to handle the low temperatures of liquefied natural gas. So LNG stands for liquefied natural gas. Tanks on these ships are insulated to limit the amount of LNG that boils off or evaporates. This boil of gas is mostly used to supplement fuel for these carriers or the ships. LNG carriers are about 300 meters long and require a minimum water depth of at least 40 feet when fully loaded. Liquefied natural gas is becoming increasingly popular as an alternative to petroleum for power generation because its reserves are as plentiful as those of oil, and it is also attractive as a clean source of energy. With LNG carrier services in effect acting as maritime pipelines, the consistent adherence to sailing schedule is of great importance to utility companies, which are responsible for the supply of electric power and gas. As the economies of the Asian countries and Southeast Asian nations are growing rapidly, so is their energy consumption and demand for LNG. Also, since LNG is a dangerous cargo, safe navigation is of paramount importance. It's important that the carriers keep the ships in top conditions over very long contract periods. Means that the vessel's maintenance and management is becoming increasingly important. Hence, as seafarers, it is your responsibility to transport goods swiftly, safely, and accurately. Loading, handling, and unloading ocean freight are of course basic to LNG chain operations, and we place safety, accuracy, and reliability as top priorities when handling LNG projects. LNG carrier crew members who are to be engaged in these operations are expected to learn the necessary techniques in order to carry out their jobs smoothly. So what is LNG? Now when natural gas is chilled to approximately minus 160 degrees Celsius under the atmospheric pressure, it condenses into liquid, about 1/600 of gas in volume. This gas, or this liquid, is called LNG or liquefied natural gas. The weight of this colorless, transparent liquid is about 1/2 of water with the same volume. So what is the composition of LNG? It is very similar to natural gas. Similar to natural gas, LNG consists of several hydrocarbons, of which methane is the main component. Methane, the chemical formula for that is CH4, of course. Other hydrocarbons making up this compound liquid are ethane, propane, butane, pentane, plus nitrogen, which is often found in natural gas, is also dissolved LNG. However, other useless components in natural gas such as H2O, H2S, CO2 or heavy hydrocarbons are removed in the liquefying process. Composition of each hydrocarbon contained in LNG dictates the actual density or specific gravity of LNG. As a difference between LNG and natural gas, it can be mentioned that the components of LNG change while in storage in a tank. This change is caused by the evaporation of light components such as methane and nitrogen, which takes place earlier than that of heavier hydrocarbons. Thus, the concentration of heavier hydrocarbons increase while in prolonged storage with LNG, of course. Characteristics of LNG in storage and transportation. The first one is having a cryogenic temperature of about minus 160 degrees Celsius. Now, LNG will require use of suitable materials for cryogenic temperature, consideration towards expansion and contraction due to the change in temperatures, structural design with due regard to thermal stress, an effective heat insulation system with precautions taken against damage caused by low temperature needs to be followed. The volumetric reduction to about 1/600 of gas at the normal temperature due to liquefaction is the second characteristic of LNG in storage and transportation. Now, this volumetric reduction is advantageous to storage and transportation, makes it easier to be carried. Tank pressure will rise due to the boil off or evaporation of this liquid otherwise. This LNG is carried as a liquid in the state of boiling point. So when equilibrium between gas and liquid is destroyed by rise of temperature or fall of pressure, the liquid will immediately start to boil. The density of LNG is about half of that of water. It is inflammable, but combustion range of its vapor is very narrow. That means if 5 to 14 volumetric percent of LNG is present in air, it forms an explosive mixed gas. In order to prevent such a formation, considerations are given to avoiding LNG coming into contact with air by, for example, keeping the tank pressure slightly higher than the atmospheric pressure. Upon leaking into air, it rapidly evaporates and forms while vapor cloud by the condensation of moisture. Other physical and chemical characteristics are that it is a colorless and odorless liquid. It has a large latent heat of evaporation. It is very volatile, has low viscosity, high dielectric power and extremely poor conductor of electricity. It can easily be charged even by static electricity. It has no causticity and no toxicity. It has almost no solubility in water and has a small surface tension. And the LNG chain of operations, if it can be described very simply, is the relation between from the gas fields to a consumer, and that is the link provided by the LNG chain. It is impossible to stabilize the supply of LNG if it is lacking in any one of them. So as you can see, the LNG operations or LNG chain of operations basically comprises of the LNG or the hydrocarbon being extracted in the gas fields and then being sent to the liquefaction plant where it is liquefied for safe carriage. Then it is sent to the loading terminal where the loading terminal actually loads the LNG in form of liquid onto the LNG carriers or ships, from where they go into the discharge port or the unloading terminal. At the unloading terminal, they again discharge the LNG in the city gas fabrication plant or the electric power plant, and finally it reaches the consumers for whom the LNG has been carried at sea. If I talk about the design standards and ship types, the overall layout of a gas carrier is very similar to that of the conventional oil tanker from which it has actually evolved. The cargo containment and its incorporation into the hull of the gas carrier, however, is very different due to the need to carry its cargo under pressure or refrigerated or under a combination of pressure and refrigeration. Gas carriers designed for pressurized cargoes can usually be identified by cylindrical or spherical tanks, which may project through the deck. That is why LNG carriers are easily recognized as sea. Similarly, The LNG carrier with spherical tanks protruding above the main deck can be easily recognized by its distinctive profile and much larger size. Gas carriers designed to carry their cargo at atmospheric pressure in prismatic tanks are not easily distinguishable from oil tankers except by their freeboard, which is significantly greater. This greater buoyancy results from cargoes of a much lower density than most oils and the requirement to have totally segregated tanks for ballast. Some of the factors to be taken into consideration which affect the design of gas ships or LNG ships are type of cargo to be carried, the condition of carriage, whether you want to carry the cargo fully pressurized, semi-refrigerated or fully refrigerated, the type of trade, which in turn determines the degree of cargo handling flexibility required by the ship, and the terminal facilities available when loading or discharging the vessel. Perhaps more than any other single ship type, the gas tanker encompasses many different design philosophies. As we go along in the presentation today, you will be able to see the different kind of ships and how they are designed. You can see one here and you will see more in the subsequent slides. Cargo control room on LNG tankers usually is incorporated in the accommodation or rather in the superstructure, or they are situated on the deck above the compressor room. In cargo control room, there are all control, communication and safety equipment. All operations for the loading of cargo are controlled and monitored from the cargo control room. The loading of LNG cargo and simultaneously deballasting are carried out in a sequence. During the loading operations, communications must be maintained between the ship's cargo control room and the port terminal. Telephone and signals for the automatic actuation of the emergency shutdown from or to the ship should also be maintained. New LNG ships are equipped with automatic integration system. This system includes cargo and ballast operations, machinery and electric generation plant operations, and some other independent control systems that are interfaced with the cargo and machinery spaces or other systems. Cargo system is capable of controlling and monitoring of the cargo and ballast, auxiliaries and valves. Automatic sequence control logic programs are provided for each cargo and ballast operation, and displays are composed of overviews, operational graphics, monitoring graphics, operational guidance graphics, and alarm displays. Emergency shutdown, cargo tank protection, machinery trip, and safety systems are totally independent from the main system. Cargo operations include aeration, inerting, gas filling, cooling down, loading, discharging, boil off, gas burning, warming up, drying, all of that we'll be discussing today in today's video. Drying and aeration, well, prior to entry into the cargo tanks, the inert gas must be replaced with air. The inert gas and dry air system produces dry air with a dew point of minus 45 degrees Celsius. The dry air enters the cargo tanks through the vapor header to the individual domes. The inert gas and dry air mixture is exhausted from the bottom of the tanks to the atmosphere at vent passed by the tank filling pipes, the liquid header and the spool piece. During aerating, the pressure in the tanks must be kept low to maximize the piston effect. The operation is complete when all the tanks have a 20% oxygen value and a methane content of less than 0.2% by volume and a dew point below minus 40 degrees Celsius. Before entry, test for traces of noxious gases, carbon dioxide less than 0.5% by volume and carbon monoxide less than 50 ppm, which may have been constituents of the inert gas, are also checked for. In addition, take appropriate precautions as given in the Tanker Safety Guide and other relevant publications. Aeration carried out at sea as a continuation of gas freeing will take approximately 18 to 20 hours. Make sure during this time you take precautions to avoid concentrations of inert gas or nitrogen in confined spaces which could be hazardous to personnel. Before entering any such spaces or areas, make sure that you test for traces of noxious gases or the availability of sufficient oxygen for breathing. This operation of inerting is undertaken to ensure a non-flammable condition with the vapor of the cargo. Inerting of the cargo tanks and piping systems are performed before preparation of a ship for commercial exploitation or before going to dry dock. Dry air from the tank is displaced by inert gas until oxygen drops to about 4%. Then gassing of operation can start. The heated gas from the cargo tanks is replaced by the inert gas. Dry air is accomplished by introducing the dry air. In this operation, it is important to use reasonable margins of safety since the precise shape of flammable zone cannot be known for mixtures. The inert gas plant introduces an inert gas generator, which is a scrubbing tower unit, two combustion air blowers, a fuel injection unit, a dryer unit of refrigeration type, a final dryer unit, and an instrumentation and control system. Before I go into the inert gas generator, or rather the inert gas plant, let me just explain a little bit about this diagram as well. What you see in this diagram is showing an inerting operation. What you see is as line OA is basically indicating that the dry air from the tank is displaced by the inert gas by line OA until the oxygen drops to about 4%. The gassing of operations then start by the line AB. The heated gas from the cargo tanks is replaced by inert gas by line CD until the dry air is accomplished by the line DO. So this is what keeps the cargo tanks inert for safe operations to take place and so that an explosive mixture doesn't develop. I have already told you the essential parts of an inert gas plant or inert gas generator. The connection to the cargo piping system is made through two non-return valves and a spool piece. Inert gas is produced by the combustion of oil with air, followed by further treatments in order to obtain the required qualities and properties. Gas oil is supplied to the combustion chamber by the fuel oil pump and air from the air blowers. Good combustion is essential for the production of a good quality soot-free low oxygen inert gas. The products of the combustion are mainly carbon dioxide, water and small quantities of oxygen, carbon monoxide, sulfur oxides and hydrogen. The nitrogen content is generally unchanged during the combustion process, and the inert gas produced consists mainly of 86% nitrogen and 14% carbon dioxide. Initially, the hot combustion gases produced are cooled indirectly in the combustion chamber by a seawater jacket. Therefore, cooling of the gases mainly occurs in the scrubber section of the generator, where the sulfur oxides are washed out. The seawater for the inert gas generator is supplied by one of the ballast pumps. Now, why I am telling you this is in the exams, if you are ever asked to draw and explain an inert gas generator, then this is a drawing that you may draw. It's quite simple and very clear. There is no complicated parts to this drawing. You can see that I have drawn all these parts either in circular shapes or triangular or rectangular shapes. I am myself not very good at drawing diagrams, so I don't expect you to do the same. Make sure that you draw the inert gas generator as this block diagram, and then as I explain the role of each of these parts, you can just write a line about each of these parts, and I can assure you it will be enough for you to pass your exams. Before delivery out of the generator, water droplets and trapped moisture are separated from the inert gases by a demister. Further removal of water occurs in the intermediate dryer stage, where the refrigeration unit cools the gas to a temperature of about 5 degrees Celsius. The bulk of the water in the gas condenses and is drained away, with the gas leaving this stage by demister. In the final stage, the water is removed by absorption process in a dual vessel desiccant dryer. The desiccant dryer unit works on an automatic changeover cycle, where the out-of-line desiccant unit is first reactivated with warm dry air which has gone through the reactivation dryer system. A pressure control valve located at the outlet of the dryer unit maintains a constant pressure throughout the system, thus ensuring a stable flame at the generator. Dew point and oxygen content of the inert gas produced are permanently monitored. The oxygen level controls the ratio of the air to fuel mixture supplied to the burner. The oxygen content must be below 1% by volume and the dew point will be minus 45 degrees Celsius. Both parameters are displayed locally as well as remotely. For delivery of inert gas to the cargo system, two combined remote air operated control valves operated through solenoid valves are fitted on the distribution system. These valves are the purge valve and the delivery valve. The inert gas generator can produce dry air instead of inert gas with the same capacity. However, for the production of dry air, there is no combustion in generator, there is no measure of oxygen content, and the oxygen signal is overridden when the mode selector is on dry air production. After the processes of cooling and drying, and if the dew point is correct, the dry air is supplied to the cargo system through the delivery valve. The combustion air is supplied to the main burner by root type blowers, each supplying 50% of the total capacity of the generator. The quantity of combustion air to the burner can be manually adjusted by a regulating valve in the excess air discharge line. Fuel is supplied at a constant pressure by the gas oil electric pump, which has a built-in pressure overflow valve. Before ignition or startup of the unit and with the pump running, all the fuel is pumped back via this fuel oil overflow valve, which also serves to regulate the delivery pressure of the pump. The main burner is ignited by a pilot burner. The main fuel oil burner is of the high pressure atomizing type. The fuel is directed to the burner orifice through tangential slots, which imparts a rotation motion, ensuring that the fuel leaves the burner as a thin rotating membrane which is atomized just after the nozzle. After lie-up or dry dock, the cargo tanks are filled with inert gas or nitrogen. If the purging has been done with inert gas, the cargo tanks have to be purged and cooled down when the vessel arrives at the loading terminal. This is because, unlike nitrogen, inert gas contains 15% carbon dioxide, which will freeze at about minus 60 degrees Celsius and produces a white powder which can block the valves, filters and nozzles. During purging, the inert gas in the cargo tanks is replaced with warm LNG vapor. This is done to remove any freezable gases such as carbon dioxide and to complete the drying of the tanks. LNG liquid is supplied from the terminal to the liquid manifold. It is then fed to the LNG vaporizer and the LNG vapor produced is passed at plus 20 degrees Celsius to the vapor header and into each tank. The LNG vapor is lighter than the inert gas, which allows the inert gas in the cargo tanks to be exhausted up the tank filling line to the liquid header. The inert gas then vents to the atmosphere. This operation can be done without the compressors. The operation is considered complete when the methane content as measured at the top of the cargo filling pipe exceeds 80% by volume. The target values for nitrogen gas and inert gas is equal to or less than 1%. These values should be matched with the LNG terminal requirements. This normally entails approximately 2 changes of the volume of the atmosphere in the cargo tank. After the cargo tanks has been purged, dried and gassed up, the headers and tanks must be cooled down before loading can commence. The cool down operation follows immediately after the completion of gas filling, using LNG supplied from the terminal. The rate of cool down is limited for the following reasons. To avoid excessive pump tower stress, vapor generation must remain within the capabilities of the compressors to maintain the cargo tanks at normal working pressure and to remain within the capacity of the nitrogen system to maintain the primary and secondary insulation spaces at the required pressures. LNG is supplied from the terminal to the manifold cool down line and from there directly to the spray header which is open to the cargo tanks. Once the cargo tank cool down is nearly completion or nearing completion, the liquid manifold crossovers, liquid header and loading lines are cooled down. Cool down of the cargo tanks on membrane ships is considered complete when the mean temperature is of -130 degrees Celsius or lower. Cool down of the spherical cargo tanks is considered complete when the mean temperature at equator is -125 degrees Celsius or lower. When these temperatures have been reached and the custody transfer system registers the presence of liquid, bulk loading can begin. Vapor generated during the cool down of the tanks is returned to the terminal by compressors and the vapor manifold as in the normal manner for loading. During cool down, nitrogen flows to the primary and secondary spaces on membrane ships and to annular space of spherical tanks will significantly increase. It is essential that the rate of cool down is controlled so that it remains within the limits of the nitrogen system to maintain the primary and secondary insulation space pressures between 2 and 4 millibar. In annular space of spherical tanks, pressure is set at about 5 millibars. Once cool down is completed and the build-up to bulk loading has commenced, the tank membrane will be at or near to liquid cargo temperature and it will take some hours to establish fully cooled down temperature gradients through the insulation. Consequently, boil off from the cargo will be higher than normal. Cooling down the cargo tanks on membrane ships from +40 degrees Celsius to -130 degrees Celsius will require a total of about 800 metric cube of LNG. Cooling rate is 12 degrees per hour. Maximum permissible cooling rate for spherical tanks is 8 degrees Celsius per hour for the first 100 degrees Celsius cool down period and 4 degrees Celsius for the rest of the period. In order to protect the tank shell against high thermal stresses, recommended temperature difference of tank equator and skirt must be respected. The pre-operational procedures must be discussed with the terminal operators during loading operations. The information exchange between terminal and ship is required and relevant checklists should be completed. Emergency shutdown systems or ESD tests must be carried out. LNG is taken through liquid line and directed into cargo tanks. Normally when loading cargo, generated vapor is returned to the terminal by means of the compressors or shore compressors. The pressure in the ship's vapor header is maintained by adjusting the compressor flow. Ship's tank pressure must be observed. Loading rates should be reduced if difficulties are experienced in maintaining the correct tank pressure. On membrane ships, the pressurization system of the insulation spaces must be in operation with its automatic pressure controls. The secondary level indicating system should be maintained ready for operation. The temperature recording system and alarms for the cargo tank barriers and double hull structures should be in continuous operation. The gas detection system and alarms must also be in continuous operation. On the end of loading operation, loading rates must be reduced as previously agreed with the terminal in order to just top off the tanks. The liquid remaining in headers can be blown into the ship's tank by injecting nitrogen into the loading arms. The maximum allowable filling limits of cargo tanks should be respected without hesitation. Cargo loading can be carried out using a vapor line and a liquid line. We sometimes call it vapor header and liquid header. Where loading is carried out with a vapor return facilities, liquid is taken on board through the liquid header and directed into the cargo tanks. Vapor generated are returned ashore via the vapor return connection using the cargo compression of the LNG carrier in order to control the cargo tank pressure. Close watch should be kept on ship's cargo tank pressure. This is the reason why this operation is done on the closed cycle, not to dispose LNG vapors at the atmosphere. During a sea passage, when the cargo tank contains LNG, the boil off from the tanks is burned into the ship's boilers. The cargo tank boil off gas enters the vapor header. It is then directed to one of the compressors, which deliver the gas to the boil off or warm up heater. The heated gas is delivered to the boilers at a temperature of about plus 25 degrees Celsius. The compressor speeds and inlet guide vane position is governed by fuel gas demand from the boilers and cargo tanks pressure. The system is designed to burn all boil-off gas normally produced by a full cargo and to maintain the cargo tank pressure at a predetermined level. If the propulsion system plant steam consumption is not sufficient to burn the required amount to boil off, the tank pressure will increase and eventually the steam dump will open, dumping steam directly to the main condenser. The main dump is designed to dump sufficient steam to allow the boiler to use all the boil off produced even when the ship is stopped. The steam dump is designed to open when the normal boil off value is 5% above the original selected value and when the tank pressure has reached the pre-selected dump operating pressure. The cargo and gas burning piping system is arranged so that excess boil off can be vented should there be any inadvertent stopping of gas burning in the ship's boilers. The automatic control valve vents the excess vapor to atmosphere. If the gas header pressure falls to less than 40 millibars above the primary insulation, space pressures, an alarm will sound. In the event of automatic or manual shutdown of the gas burning system, or if the cargo tank pressure falls to 5 millibars above the insulation spaces pressure, valve will close and the gas burning supply line to the engine room will be purged with nitrogen. When the ship arrives at the LNG receiving terminal and when ships and terminal lines are connected, pre-operational tests can be carried out. Unloading operation begins with one cargo pump and low rate to cool down ships and terminal lines. Cooling down operation lasts about 1 hour when other pumps can be started and unloading rate increased. Cargo centrifugal pumps should be started against partially open valves in order to minimize the starting load. Thereafter, the discharge valve should be opened gradually until pump load is operating within design parameters. Cargo discharging takes about 15 to 16 hours. All pumps run in parallel. The tank pressures tend to fall as cargo is being removed from tanks. Vapors produced by remaining cargo boil off are insufficient to balance the liquid removal rate. To maintain normal tanks pressure, the gas may be provided from terminal via the main gas line or it can be produced by using the ship's forced vaporizer. If it is being produced by the ship's forced vaporizer, liquid is taken from the liquid line and diverted through the vaporizer. Towards the end of the discharging, unloading rate should be reduced, usually by stopping one pump of each tank. On completion of cargo discharge, liquid line must be drained and manifold valve closed. Then terminal loading arms can be disconnected from the ship's manifold. From that moment, ship takes care of tank's pressure by burning gas in ship propulsion boilers. Cargo unloading can be carried out using a vapor header and a liquid header, same as a loading operation. Unloading operation is carried out with ship's submerged pump in each tank. In order to control the tank pressure, LNG in cargo tanks can be sent to storage tank off shore side and vice versa, with return gas blower to ship's tank. During ballast operation or ballast passages on LNG carriers, it is usual practice to retain some liquid in tanks after discharge. This liquid is used to maintain tanks in cold condition in order to be ready for next loading. The quantity of retained liquid depends on the size of the ship, type of cargo containment system, and length of voyage. All LNG vessels with spherical or membrane tanks are equipped with spray cool down pumps. The frequency of this operation is much more demanding on LNG tankers with spherical cargo containment system in order to have equator temperature at minus 125 degrees Celsius, what is required before loading operation. A characteristic of the cargo tanks of the membrane type is that as long as some quantity of LNG remains at the bottom of the tanks, the temperature at the top will remain below -50 degrees Celsius. However, if the ballast voyage is too long, the lighter fractions of the liquid will evaporate. Eventually, most of the methane disappears and the liquid remaining in the tanks at the end of the voyage is almost all LPG with a high temperature and a very high specific gravity which precludes pumping. Thus, operators should consider heel aging for coolant when ballast voyage is too long. Due to the properties of the material and due to the design of the membrane cargo containment, cooling down prior to loading is theoretically not required for the tanks. However, to reduce the generation of vapor and to prevent any thermal shock on the heavy structures, loading takes place when the tanks are in a cold state. The remaining liquid level of membrane tanks must never be above 10% of the length of the tank, and the quantities can be calculated by considering a boil-off of approximately 45% of the boil-off rate under laden voyage condition and the need to arrive at the loading port with a minimum layer of 10 centimeters of liquid spread over the whole surface of the tank bottom. Additional cool down should be carried out at the LNG terminal when the cargo tank temperature is higher than -130 degrees Celsius. Maintain the cargo tanks at cold during the ballast voyage by periodically spraying the LNG so that the average temperature inside the tank does not exceed -130 degrees Celsius. It is obvious that spraying will generate more boil-off than without tanks cooling down. The quantity of LNG to be retained on board will have to be calculated with enough margins to avoid the situation at mid-voyage where the residual is too heavy for the pump to operate. If conservation of bunkers is requested, it is essential to ensure as much boil-off gas as possible to supply boiler fuel demand, thus keeping fuel oil consumption to a minimum. Tank warm-up is part of the gas freeing operations carried out prior to a dry docking or when preparing tanks for inspection purpose. The tanks are warmed up by heated LNG vapor. The vapor is recirculated with the compressor and heated with the cargo heaters to 70 degrees Celsius. In a first step, hot vapor is introduced through the filling lines to the bottom of the tanks to facilitate the evaporation of any liquid remaining in the tanks. In the second step, when the temperatures have a tendency to stabilize, hot vapor is introduced through the vapor piping at the top of the tanks. Excess vapor generated during the warm-up operation is vented to atmosphere when at sea or burning in the boiler. The warm-up operation continues until the temperature at the coldest point of the secondary barrier of each tank reaches 5 degrees Celsius. The warm-up operation requires a period of time dependent on both the amount and the composition of liquid remaining in the tanks and the temperature of the tanks and insulation spaces. Generally, the warm-up will require about 48 hours after vaporizing the remaining liquid. Initially, the tank temperatures will rise slowly as evaporation of the LNG rolling and pitching of the vessel will assist evaporation. Gas burning should continue as long as the tank pressures start to fall. The primary and secondary insulation spaces are filled up with dry nitrogen gas, which is automatically maintained by alternate relief and makeup valves as the atmospheric pressure or the temperature rises and falls under a pressure of between 2 millibar and 4 millibar above atmosphere. The diagram is showing you the nitrogen distribution system in membrane type of ships. The nitrogen provides a dry and inert medium for the following purposes: to prevent formation of a flammable mixture in the event of a LNG leak, to permit easy detection of a LNG leak through a barrier, and to prevent corrosion. Both primary and secondary insulation spaces of each tank are provided with a pair of relief valves which open at a pressure sensed in each space of 10 millibar above atmospheric pressure. Nitrogen produced by generators and stored in a pressurized buffer tank is supplied to the pressurization headers through makeup regulating valves. From the headers, branches are led to the insulation spaces of each tank. Excess nitrogen is vented through exhaust pressure control valves to vent mass from the primary and secondary insulation spaces. Two nitrogen generators installed in the engine room produce the gaseous nitrogen, which is used for the pressurization of the barrier insulation spaces, as seal gas for the compressors, fire extinguishing in the vent mast, and for purging the fuel gas system and various parts of the cargo piping. The two high capacity units are able to produce high metric cube tons of nitrogen. The operating principle is based on the hollow fiber membranes through which compressed air flows and is separated into oxygen and nitrogen. The oxygen is vented to the atmosphere and the nitrogen stored in about a buffer tank about 30 metric cube in capacity. Each unit consists of a screw compressor, cooled from freshwater cooling system, single stage air water separator, 3 air filters arranged in series, electric heaters before passing into the membrane units, as well as an oxygen analyzer after the membrane monitors the oxygen content, and if out of range above 4% redirects the flow to the atmosphere. On the older generation of LNG vessels, nitrogen is stored as liquid in double shell tank and vacuum and perlite insulated. The nitrogen storage usually include 1 or 2 storage tanks with vaporizer and heater. Vaporized and heated nitrogen is distributed to consumers. LNG tanker of 125,000 metric cube capacity normally has nitrogen storage tank of about 70 metric cube. Tank pressure is 3 bars, liquid temperature is minus 196 degrees Celsius. Emergency cargo pump installation. In the event that both main pumps have failed in cargo tank on membrane ships, the emergency cargo pump is used. The pump is lowered into the emergency cargo pump column for that tank. Cables and a connection to the local junction box are used to power the pump. The pump, when lowered to its final position, opens the foot valve in the column and the LNG can be pumped out. The pump discharges into the column and to the liquid line. When all equipment, pump, cables, electric connection box and accessories are in position near the tank in which the pump is to be installed, the derrick needs to be prepared to lift the pump and start the pump installation. The cargo tank will inevitably contain LNG, therefore the column into which the emergency pump is being lowered must be evacuated. This is achieved by injecting nitrogen into the column. In the case of a full cargo tank, a pressure of about 20 to 30 millibar is required. The nitrogen forces the liquid out through the foot valve located at the bottom of the column. In the case of cargo pumps failing on spherical tanks, the unloading can be carried out by pressurizing the tank and forcing the liquid into one or more other tanks. Spray pumps can be used to create the pressure that is required for unloading. In case there is an inner hull failure, ballast water leakage from the wing tanks to the insulation spaces can occur through fractures in the inner hull plating. If the leakage remains undetected and water accumulates in these spaces, ice will be formed. Ice accumulation can cause deformation and possible rupture of the insulation. The resultant cold conduction paths forming in the insulation will cause cold spots to form on the inner hull. The pressure differential caused by the head of water building up in the insulation space may be sufficient to deform or even collapse the membrane into the cargo tank. To reduce the risk of damage from leakage, each cargo insulation space has been provided with water detection units. At the bottom of cofferdams, there is a bilge well for each tank insulating space. Each of these wells is fitted with water detection units. Each detector is of the conductivity cell type, which causes a change in resistance due to the presence of humidity from the ingress of seawater and activates an alarm. The bilge well serves as the inlet for the nitrogen supply pipe to the insulation space. This supply pipe also acts as a manual sounding pipe to the bilge well. Each bilge well is connected to draining pipe system with a pneumatic pump situated in the forward and aft pipe duct for discharging the water to deck level and then overboard by means of a flexible hose. After the maximum possible water has been discharged from this insulation space, appreciable moisture will remain in the insulation and over the bottom area. Increasing the flow of nitrogen through the space can assist drying out the insulation. This should be continued until the moisture level is below that detected by the water detection system before any cargo is carried in the affected tank. What happens during gas leakage detection? Well, fatigue fractures in the primary insulation membranes are generally small and will pass either vapor only or a sufficiently small amount of liquid which will vaporize as it passes through the fracture. It is, however, possible that a large failure of the membrane could occur allowing liquid to pass through and eventually gather at the bottom of the primary insulation space. A small leakage of vapor through the membrane may not be readily obvious. However, indications are likely to be of a sudden rise in the percentage of methane vapor in one primary insulation space. Some porosity in the primary barrier weld will allow the presence of methane vapor in the primary insulation space. The amount of this vapor should be kept to a minimum by the purging of nitrogen gas. If a fracture occurs in the primary insulation barrier below the level of the liquid in the tank, the vapor concentration will increase slowly and steadily. If the fracture is above the liquid level, the concentration will exhibit a fluctuating increase. The vapor concentration in each primary insulation space is recorded daily to detect any small and steady change. No temperature change will be obvious unless the fracture is in the immediate vicinity of the sensors below the cargo tank. Leakage of methane vapor into the primary insulation space presents no immediate danger to the tank or vessel. In case of liquid leakage, a major failure in the primary membrane allowing liquid into the primary insulation space will be indicated by either a rapid increase in the methane content of the affected space or a rise in the pressure in the primary insulation space or accompaniment by continuous increased venting to atmosphere, general lowering of inner hull steel temperatures or a low temperature alarm at all temperature sensors in the insulation below the damaged cargo tank. If a major failure of the membrane occurs, liquid from the cargo tank will flow into the primary insulation space until the levels in both compartments are equal. When the contents of the cargo tank are discharged, unless the LNG in the primary insulation space can drain sufficiently quickly to the cargo tank, a differential liquid head will build up, tending to collapsing of the membranes of the tank. Before discharging a tank with a major failure in the primary membrane, it is essential that the primary membrane is punched so that the liquid can freely flow back into the tank from the primary insulation space. In this way, no hydrostatic head occurs in the primary insulation space, which could cause a damage to the primary membrane support. The punching device is a 30 kilograms messenger which is dropped down the float gauge tube so as to punch a hole in the primary membrane at the base. The base of the float gauge tube is fitted with a split perforated base to allow the messenger to penetrate through to the membrane. The membrane is fitted with a thin diaphragm and the plywood insulation boxes are thinner than normal to allow the messenger to penetrate fully.